Guys, in this video I'm going to look at the 2024 trial exam from the Northwest Province. I'm going to do the entire question paper. Guys, if you are new here, welcome, and please don't watch my videos without subscribing. If you're returning, welcome back. Thank you so much for tuning in. Guys, let's cut the chase. Question 1, I'm going to start with question 1 till question 9. It says, which one of the following compounds is a ketone? And we're given the condensed structure. The ketone, it's like that. Its functional group structure, it's going to be CO, that is within the carbons. So can we look at A? That can be a ketone because it's CO within the carbon. That cannot be a ketone because it has 2 oxygen, and in the CHO, which is the terminal, the ketone, it cannot be in the terminal, and that one is the alcohol. So the correct answer is A here. Now it says, consider the following flow diagram represent organic compound. We have compound X, and then what is added there in that compound X? We added the HBr. So which means this one is an addition, right? So what happened there, it's going to be 2-bromo 3-methyl, right? So if it's 2-bromo and methyl butane, that means it cannot, the compound X, it cannot be this, it cannot be. Why it cannot be that? The methyl is in 3, the methyl here is 2, and the methyl is in 3, and it's 3-methyl and 2-bromo, which is, it cannot be that one as well. That means this one is an alkene, right? It must be an alkene. It must have a double bond, so that double bond is going to be removed by adding that. So it cannot be that. So let's look at this one, 2-methyl but 3N, right? So it cannot be that because this is 3-methyl, the methyl is in carbon 3, and this one, the methyl is in carbon 2. It cannot be that. Now this is 3-methyl but 2Na, that's correct, right? So this one is it's like this. This is a butane, and the double bond is there, and in carbon 2, in carbon 3, let's say this is 3, here's a methyl there, right? So when you add the HBr, the Br, the hydrogen, let me use another pen, when you remove that, the hydrogen is going to be there and the Br is going to be there, right? So that's there. Now let's look at which one of the following pairs of reactant can be used to prepare the ethyl propanoate. This one, the ethyl propanoate, is the what? Is an ester. So the ethyl, it must be an ethanol. So it cannot be that. That's not an ethanol. That's not an ethanol. And then the propanoate, it must be a propanoic acid. So here's the propanoic acid and an ethanol, and an ethane. It can be that. It can be that. So the answer there is C. Now, which one of the following compounds will enable butan 1O to undergo the elimination? So when we eliminate, which means we are removing the water. So when we eliminate it there, we are removing the OH and the hydrogen that makes what? Water. That's what we are removing there. So we are removing by the concentrated what? Sulfuric acid. We cannot remove by that. We cannot remove by the dilute nitric acid. We cannot even the dilute base. We remove when we add water, we use sulfuric acid. When we eliminate water, we use sulfuric acid. So the answer there is B. Right, let's look at 1.5. When zinc carbonate reacts with an excess hydrochloric acid. So if this hydrochloric acid is in excess, that means the zinc carbonate is a what? Is a limiting, right? It's an excess and it's limiting. The graph below are obtained under two different conditions. So we have two graphs here. The graphs that, guys, when we add the zinc carbonate with what? Hydrochloric acid, it will give you zinc chloride plus carbon dioxide and water. So the hydrogen gas there has been produced. So this is the graph of hydrogen gas, but these, we have two graphs there. We have graph R and graph S. So the initial graph here is S. And here it says the change in the graph from S to R could be brought by, so the initial, it was that, the second graph, it's that one. So what causes that? A decrease in concentration of hydrochloric. When you decrease the concentration of hydrochloric acid, it cannot give you a graph R from S to R. Increase in the mass of calcium carbonate. That's correct. So the calcium carbonate is the what? Is the limiting. So when you increase the limiting there, that means the production of carbon dioxide, and there will be more carbon dioxide will be produced there, right? And then that's not even adding a catalyst, it won't give you more carbon dioxide. Decreasing the particle of zinc carbonate, it won't give you that. So the answer there is B, right? Now 1.6, it says the reaction represented by the balance equation below reaches equilibrium in a closed container. So it's a equilibrium in a closed container. We're given the delta is less than 0. That means the forward is exo and the reverse is endo, right? Now it says, how will the equilibrium be affected if the volume of the container is increased? Okay, let's stick to that. If the volume of the container is increased, that will affect pressure. The volume is increased and the pressure will decrease. So a decrease in pressure favors the side with the least number of moles. So with the side least number of moles here, there's no least number of moles. Oh, the number of moles here, it's 1, that makes 2 and 2. So there will be no change. So the volume will be no change or no effect. There will be no effect by increasing volume. It says increase volume at constant temperature and then the temperature is increased. So when the temperature is increased, we know what is favored. The reaction favors the what? The endothermic reaction. So let's look at our answer. So our endothermic reaction is what? Is reverse, right? The reverse is endo, the forward is exo. So the effect of increase in volume has no effect. So the answer here is between this and this and this. The volume, it won't have an effect. So an increase in temperature will favor what? Reverse. So the answer here is what? Is A. I hope I do make sense. Okay, let's look at it says a nitric acid is that, and ammonium hydroxide is that. Nitric acid is a strong acid, ammonium hydroxide is a weak base, right? It says the equivalence point is a point is the point in titration where the acid or base completely react, right? That's the definition of the endpoint. It's the equivalence point. It's where the acid or base completely react with the acid or base. So here in this option, that is the point where the titration of concentration of an indicator changes. No, the indicator changes. We call that it's the end point. and then the number of moles of an acid is equal to the number of moles of a base. That's correct. In the end point, the number of moles of a base is equal to the number of moles of an acid. So the concentration of a base is not equal to the concentration of an acid. The pH is not equal to 7, which is neutral. So the answer here is B. Right? 1.8, it says consider the equation. We have water and that reactant that we do not know. We are given the product, there's OH and that. So this simply means that if you had water and you have OH now in the place of water, that means the water has donated a proton there. So once it donates a proton, it will be that. So that means A here is HSO4 minus. So the HO4 minus, when it gets the proton from water, it becomes what? It becomes H2SO4, which is this. So it says A is represent a base. This is a base, right? And this will be what? An acid. So it represents a base, right? It can be an acid. It can be an acid. So does it represent a base having that formula? No, it represents a base having that formula. The answer is A, as I've mentioned there. 1.9, the second last question. Consider the following chemical reaction. We have Pb in a solid state now. It's an ion and 2 electrons. That means here what is happening there is oxidation. And then here we have the electron. We see by the electron there in the reactants, and then that means there it's a reduction, right? Which one is reduced here? It's very important here. Look at hydrogen, it's +1, and the oxygen is 0, and the oxygen is -2, and yeah, let's look at the hydrogen. The hydrogen here is +1. Look at the hydrogen, there's no change, and look at the oxygen from 0 to -2. That means what is reduced here is oxygen. It's a reduction, right? So what is reduced here is oxygen, not hydrogen. So what is oxidized there is lead. Now it says which one of the following combination is correct for X and Y. So we know this one is what is oxidized. So it cannot be in reaction X. This cannot be reduced, it's oxidized, right? And as I've mentioned here, it's not hydrogen that is reduced, it's oxygen that is reduced here, so that is wrong. So Pb is what is oxidized, and oxygen is what is reduced. Pb cannot be reduced, hydrogen is not oxidized. So the answer here is what is C. Last question. Which one of the following correctly shows the gases produced at the different electrode during the electrolysis of concentrated sodium hydro? So in the electrolysis, guys, there, so we have, let's say we have, this is going to be the positive, it's going to be what? An anode. In the electrolysis, the negative, it's going to be a cathode, right? So if we have the sodium chloride solution there, we'll have sodium ion, chloride ion, and water there, and water. So what's going to happen? The chloride ion will be attracted there, right? Once it attracted there, that means it's going to what? Oxidize. It's going to oxidize, which is it's going to form a chlorine gas with 2 electrons. So there will be a gas, chlorine gas there, the yellowish green there. So in there, yeah, so this is an anode. So in the anode there will be a chlorine gas. One of our options is those two. And then between the water and the sodium ion, it's going to be water that is going to be it's going to be reduced there. So when water is reduced there, it's going to form bubbles there, which is the what? The hydrogen gas. It's going to form the hydrogen gas there, the water. So one of the options there, it's that one. So in the cathode there's hydrogen gas, and the anode there will be a chlorine gas. So all these, they are not options. All these, so the best option is that one. I hope that makes sense, guys. Cheers. Let's go to question 2. Let's look at question 2. Question 2, it's a nomenclature. It says a letter A to F in the table below represents 6 organic compounds. It's very important to understand what are these organic compounds. Looking at them before you answer the question. The compound A, if you look at it, has a COO. That means it's a what? It's an ester. It's an ester. And B, if you look at B, the functional group that is there, it's a carbonyl that is within the chain, that's the ketone, right? And C, we have a 2-fluoro 3,5 dimethylhexane, that's the haloalkane, right? And then D, if you look at D, D, that's the alkene. We have an alkene there. If you look at E, we have a carbonyl, and the carbonyl, it's the terminal, which is, this is there, and we have an H there. This is in aldehyde, right? That's the formyl group, the name of the functional group structure. And F, the last one, butanoic acid, it's a carboxylic acid. Sorry. Now 2.1, it says letter of the compound that belongs to the haloalkane. Which one is the haloalkane? Here is C. The structural formula of the functional group of F, which is the carboxylic acid, it's the carbonyl with the OH, and then there must be a bond there, like that. That's the structural formula for the functional group. Letter of a compound that represents an unsaturated, it's a multiple bond, which is, it's going to be this, the alkene only. Don't confuse and say this and this is an unsaturated. So the letter there is D, right? And then the name of the functional group of E. What is the functional group of E? The name of the functional group of E, it's aldehyde. Aldehyde, the functional group, not the name of the functional group structure. If they said name of the functional group structure, it was going to be what? Formyl. Now it says the name of an inorganic acid needed to prepare a ester is prepared by an inorganic acid. What is an inorganic acid there? It's a sulfuric acid. They wanted the name. It's a sulfuric acid. Right? Letter 2.6, it says letter of the compound that represent an aldehyde. Letter of a compound that represent an aldehyde. Guys, the name of the functional group, this one is not, it's not an aldehyde, it's a formyl. Right? The answer is not an aldehyde, it's the formyl. The letter that represents an aldehyde there, it's E. Right? The empirical formula for compound A, let's look at compound A. Compound A, it has, we said it's an ester, right? It's an ester. It has how many carbons? 1, 2, 3, 4. It has 4 carbons and 3, 5, 8, and 8 hydrogen and O, and 2 oxygens there. So the empirical formula for that, that's the true formula for that ester. So the empirical formula for that, it's 4 carbon and 8 oxygen and 2, so it's going to be 2 carbon and 4 hydrogen and 1 oxygen. So it's the simplest ratio. It's the simplest ratio of 8 is to 4 is to 2. It's going to be, no man, it's 4 is to 8 is to 2. The simplest ratio for that, it's going to be 2 is to 4 is to 1, right? Structural formula for compound C. Which one is compound C? Is this one. The structural formula for that one, let me draw it here. It's a hexane, 1 2 3 4 5 6. The parent is the hexane, it's going to be 6 1 2 3 4 5 6. And then it says the fluoro, it's in carbon 2. Here's the fluoro in carbon 2. So the carbon 2, it can be this one if you like. And then 3 and 4, it's a dimethyl, right? 3 and 4, there are 2 methyls there. So it's gonna be like that, guys. Because of saving time, I'm not drawing the hydrogens there. Okay, let me draw them. Please don't forget to draw the hydrogens there, like that. You lose a mark if you have no hydrogens there, right? Now the IUPAC name of compound B. IUPAC name of compound B, let's zoom it a bit. So the compound B, guys, the compound B, it's a ketone. So the longest chain here, it's 1 2 3 4 5. 1 2 3 4 5 6, right? 1 2 3 4 5 6, right? So we cannot say 1 2, okay, it's the shortest, the longest is that one. So we're going to start at the end. So we have two ends, this end and this end. We're going to start with the side with the carbon now, which is the functional group. This is going to be carbon 1 2 3 4 5 6. So the name of that is going to be we have carbonyl, we have methyl there, and the methyl in the same carbon, carbon 4. So the name of that, it's going to be 4,4 dimethyl, and the parent is what? Is hexane, because there are 6. And then where's the ketone in carbon 2? The carbonyl, right? That's the name of that. And the last question, it says letters of compound that are functional isomer of each other. Letter of compound that are functional isomer of each other. The functional isomer, you need to understand the definition. It's the compounds with the same molecular formula but different functional groups. So here, the compounds that are functional isomer of each other, it's ketone and aldehydes, right? And carboxylic acids and what? And esters. So let's look at the ketone and the aldehyde. Here's the ketone and here's the aldehyde. Are they functional isomer of each other? No, because how many carbons here? 1 2 3. It's 3 carbons. It has to be the same number of carbons here. So the carbons here are more. They are not functional isomer of each other. Let's look at an ester. How many carbons? 4. How many hydrogen? 8. Let's look at this one. How many carbons? 4. That means these ones are functional isomer of each other. So it's A and F. The answer is A and F. A and F. I hope I make sense, guys. Let's look at question 3. It's the physical properties and intermolecular force. The investigation was carried out to determine the relationship between the boiling point of different alkanes and one of their structural isomers. The results obtained are shown in the table below. If you look at this table, guys, we have compounds, which is the alkanes, which is the straight chains if you look at them from A to D, and their boiling points, right? Now if you look at E to G, they are isomer of these ones, right? And what type of isomers? Structural isomer. You need to understand the structural isomers, right? Structural isomer. These type of isomers are chain isomers from this one. These ones are branched, right? And this one are less branched. These are straight chain and less branched, right? The ethane, we are not given the isomer of each of it. We are given the butane, and the butane has its isomer, which is the methylpropane. How do you know the isomer? 4 carbons and 4 carbons. That's 3 carbons plus 1, it makes 4, and then the hydrogen will be the same. So the molecular formula of this will be the same. Pentane, that's 5 carbons, and butane and 1 methyl, that makes 5. So these are isomer of each other, right? And these isomers are given their boiling points. If you compare this one, butane and the methylpropane, look at the boiling point of butane, and look at the boiling point of the methylpropane, its isomer. The boiling point is less, and this one is greater. So that means the intermolecular force of this one is greater, right? The longer the chain, the greater the intermolecular force. This one is less, it has a less surface area. This one has a greater surface area. Okay, let's leave that. Let's answer the question. Define the term structural isomer. Structural isomer, it's compound with the same molecular molecular formula but different structural formula. Guys, please stick to the exam guideline. I might be paraphrasing it, but it's that. 3.2, what type of isomerism is used in this investigation? So the type of isomerism here, it's a chain isomer. So this type of structural isomer here is the chain isomer. They differ by the chain, right? Right. It says explain the difference in boiling point between butane and its isomer. So what are you going to say here in 3.3? You're going to say butane. So what are you going to talk about? Number one, look at this, it's 3 marks. So what are they compared here? It's the structure. You're going to talk about structure and talk about the energy. You're going to talk about the structure and talk about the intermolecular force. So these are the things that you need to talk about here. You need to talk about the structure, right? Let's talk about the structure first. Butane. The question, it's a butane and methylpropane, which is we are talking about these two, right? Butane has a larger surface area than its isomer. I'm just trying to shorten it. And then the next thing we're going to talk about the strength of IMF, strength of intermolecular force. A butane has a stronger London force, or you can say stronger intermolecular force than its isomer, right? Or you can say methylpropane. And then the last thing that you're going to talk about is the what? Is the energy. You're going to talk about the energy. So you're going to talk about an energy. So that means butane need more energy to overcome the intermolecular force, right? Then the isomer, its isomer, which is the methylpropane. So guys, that's very important for that. Now it says consider compound A to D. So these are alkanes, right? They differ in chain length, right? Right now it says for this part of the investigation, write down the control variable. So the control variable, it's what is not changed in these as you come from the 2 carbon, 4 carbon, 5 carbon, 6 carbon. What is the same, what is fixed there? What is fixed there is the homologous series. Homologous series or functional group. Functional group. So these are alkanes, guys. As they increase the number of carbons, they are alkanes. They don't change, which is the homologous series and the functional group is the same. What is the independent variable? The independent variable, guys, it's what makes them different. They differ by what? By number of carbons. You can say they differ by number of what? Of carbons. Or you can say they differ by the what? By the chain length. Or you can say they differ by the molecular mass, right? Or you can say they differ by the surface area. Which one of the compound A to D has the highest vapor pressure? Which one has the highest vapor pressure? The one that has the highest vapor pressure is the one with the lowest intermolecular force, which is it's A. A. The answer is A there. Explain your answer. So it's 2 marks there. So explaining your answer there, you can say A. You will talk A. It says explain your answer by referring to the intermolecular force. So you can say A has a what? Weaker. Has a weaker IMF. Weaker IMF, and you can say less energy needed. They said you talk about the intermolecular force and energy. Less energy needed to overcome the intermolecular force. Now 3.5, the second last question. Write down a conclusion for this investigation. So what is the conclusion? So the conclusion for this investigation, guys, you need to involve the dependent and independent variable. So if you look here, what can you conclude here about the dependent and independent variable? Guys, the dependent here, the dependent variable here, it will be what? The boiling point. Right, since we're given the boiling point, it will be the boiling point. And then the independent variable, we stated that is going to be the number of carbons. So you conclude, you say by the more the number of what? Carbon atoms, the higher the boiling point, right? Right, that's the conclusion in you involve the control. Okay, it's fine, you don't have to. Now it says use the molecular formula to write down the balanced chemical equation for the combustion of pentane. So the pentane, it's going to be C5 and hydrogen 12 for hydrogens. The hydrogen will be 12, and then you add what? Oxygen. That's the combustion. You add oxygen, and then it will be the product there. It will be carbon dioxide plus water, right? Carbon dioxide, and then you balance how many carbons there? 5, and how many carbons here? 1, and then you put 5 there. Right, it's balanced. How many hydrogens? It's 12, and how many hydrogens there? It's 2, and then you type 3, you put 3 there, it makes 6. And then oxygens, it's 2, and then it's 10. 5 times 2, it's 10, plus that, it's 13, right? So 13, if you put 13 in there, you say 13, and then if it's 13, but it needs to be 13 over 2, and then you times everything by 2, so it will be 2 carbon 5 H12 plus 13O2, and gives us 10 carbon dioxide plus 6 water. Right, guys, I hope I make sense by that.
Let's look at question 4. Question 4, study the flow diagram of various reaction and answer the questions that follows. We have compound A, right? So the reaction that occurs in compound A, it gives us the butane and a propane. So the only reaction that's possible for that, if you get an alkene and an alkane as the products after you've done that reaction. This reaction 1 is an elimination. And what type of elimination is that specifically? Is the cracking. So if you crack a compound, what compound A is that one? Is an alkane. So you can crack the alkane into alkene and alkane, right? You're breaking it, you're cracking it into pieces, right? And then let's look at reaction 2. You have this alkene, and reaction 2, there's a hydrogen gas there. That simply means that it's a what? It's an addition. You are adding the hydrogen there. And what type of addition is that one? Is the hydrogenation. And then if in a butene, if you add hydrogen there, it becomes a what? A butane. With hydrogens, full hydrogens. It's gonna be that. And then reaction 3, from a butane, which is an alkane, it becomes a 2-chlorobutane. 2-chlorobutane. So in the butane, there was all hydrogens, but now in the second carbon, there's a what? There's a chloro there. So it's going to be like that. In the second carbon, there's a chloro there. That means what happened? Reaction 2 is a what? Is a substitution reaction. And what type of substitution reaction? It's the halogenation. Right? And then it's a halogenation. And then from this haloalkane, we are told the only thing they didn't tell us what is compound C. So from there, reaction 5, it become a 2-butanol. So there, that's the substitution as well. And what type of substitution is that one? It's the hydrolysis, right? It become this now. In the place of the halogen, it has the what? The OH, right? We cannot analyze what is that one, and not unless they lead us, right? Okay, let's answer the questions. For reaction 1, write down the type of reaction. Reaction 1, we already mentioned that is elimination. It's elimination, it's cracking. The IUPAC name of compound A. The IUPAC name of compound A, it's going to be what? Butane. It's going to be butane. You're cracking it from a butane. It's going to be a butane, an alkane. Consider the reaction 2 and write it down. Reaction 2 is this one. It's an addition, which is the hydrogenation. What type of reaction is that one? It's an addition or hydrogenation. You write any of the two, you'll be correct. And the IUPAC name of organic compound B, it's a butane, right? It's a butane. Of compound A, guys, I think I've made a mistake here. This is not a butane. This is not a butane of compound A. Compound A, if you look at this, it's four carbons of butane and three carbons. That makes seven carbons there. So this alkane, it's supposed to be a what? A heptane. So it was a alkane that is a heptane. It's cracked to this. It has seven carbons. It's still cracked to seven carbons, but in different organic compounds, which is 4 and 3. That makes 7. So the answer here is heptane, right? I'm reminded by this one. They have the same name. It was butane and butane. I figured I was wrong. It's a butane, and then it says name a suitable catalyst. The catalyst for addition, guys, for reaction 2, for adding hydrogen there. It's 3 catalysts that you can use. It's platinum or nickel or a palladium, right? They said name, not formula. So you write the name of each. You say it's platinum or nickel or palladium, any of the 3. Now let me move this a little bit up. There's still the Northwest Province, guys. Now it says write down the type of reaction to represent reaction 3. Reaction 3, the type of reaction, guys, it was substitution from an alkane to haloalkane. We substituted, so it's substitution or substitution or what? What did we say? It's a halogenation. Now reaction IV is an elimination. Now they're giving us a hint. This one they say it's a what? Elimination, right? It's an elimination, right? It says the type of it says write down the type of elimination is that one, right? Okay. It says a reaction is an elimination. Write down the type of elimination is that one. They didn't tell us what is compound C is, but what are we going to eliminate here? What are we going to eliminate? We're going to eliminate this this chlorine, right? And this chlorine and the what? And the adjacent hydrogen, this one or this one, right? So we're going to call that type of elimination, it's a dehydrohalogenation. We are removing this hydrogen and the chlorine there. We're not removing a chlorine alone there. So with this type, it's going to be dehydrohalogenation because we removed both there. Now the reaction condition for that, it's going to be heat. It needs a heat for that, and we're going to need a concentrated strong base. We use to remove that, to eliminate concentrated strong base, which is this strong base. It's a what? It's a sodium hydroxide or the caustic potash, which is the potassium hydroxide. Now 4.4.3, it says write down the chemical equation for the formation of C using the structural formulae. So 4.4.3, remember we are coming from this haloalkane, and we remove from this one, we're going to remove the chlorine and hydrogen there. So it's going to be like this. It's the haloalkane with the chlorine there, with hydrogens, guys, don't forget the hydrogens. It's very important you lose marks. The hydrogen and the chlorine. I'm making them red because I want to remove them. So what do we use? I said we use what? We use sodium hydroxide with heat. That means heat, guys, right? And this is going to be removed, and this is going to be removed, right? So basically, this is going to be an alkene. So here there will be a double bond that is formed there. So double bond that is formed there. That's still there. Hydrogens there. And what is a byproduct? So what's basically is going to happen at this sodium, since this is in an ethanol, there's an ethanol, so it's going to split to sodium ion and hydroxyl ion. And this chlorine that you remove there is going to be chloride, and this hydrogen that you remove there is going to be hydrogen ion. So these two are going to be attracted and form a byproduct here. So this alkene is going to have a salt, and what else? It's going to have what? This hydrogen, hydrogen ion is going to be attracted to the hydroxyl and form water. So it's going to be water like that, right? That's the byproduct. I hope that makes sense. Now it says consider reaction V, which is 5, which is already mentioned what is happening there. It's a substitution from haloalkane to an alcohol. Now it says name or formula of an inorganic reactant, right? To do that substitution, guys, from a haloalkane to an alcohol, you add water. So the inorganic reagent that you use there is what? It's water. You add water or dilute base. It's a dilute what? Base. Dilute base, which is the base here. It's the sodium hydroxide or the caustic potash, right? Now it says type of alcohol represented by 2-butanol, which is this one. This one, what type of alcohol is this one? You can see it's carbon, it's bonded with the 2-carbon. It's a secondary. It's a secondary. And then your reason here, you can say 4.5.2. You can say the carbon, I'm not going to write it, guys. The carbon in which you explain that, you say the carbon, which is this one, that is bonded to the hydroxyl, is bonded to the 2 carbons. There, that's what you say. Guys, I hope that makes sense. That's it for this question. Let's look at question 5. It says reaction of magnesium and excess of dilute hydrochloric acid is used to investigate some of the factors affecting the rate of reaction. The balance equation. The balance equation for the reaction is that. So we are told the HCl is in excess. Simply means that magnesium is a limiting. It's going to be used up. Guys, whenever you add a magnesium with an acid, there will be a magnesium chloride and the hydrogen gas. Right, the table below summarizes the reaction conditions. So we have done 3 reactions here, 3 experiments. In experiment 1, they used the magnesium in a ribbon, which is in a solid state form, which is in a lower state of division, and the mass of magnesium, it was X at 25 degrees Celsius. And then now the state of division has been increased. It's a powder and the mass is the same as X at the same temperature. Already you can see which one is faster between the two. And in experiment 3, a state of division is still powder, but the mass of magnesium has been decreased, and at lower temperature. We can see this is going to be the last one. So let's arrange according to the rate of reaction, which one is going to be faster? The one that is going to be faster is going to be this one and followed by this one. So you can compare the two because they have same mass and same temperature, and they differ by the state of division. So the one that has a powder is going to be faster. That's why I rated 1. And then lastly, this is going to be the 1, because this one, it occurs at lower temperature, but it's still the powder, but the mass is what? It's smaller, right? Now let's answer the questions here. But the difference between the last one, it's going to produce the amount of hydrogen is going to be what? Little, because of this. The limiting produces the hydrogen, right? The more you add the limiting, the more the hydrogen increases. Okay, let's 5.1 define the term rate of reaction. Guys, stick to the exam guideline. The rate of reaction, guys, is the change in concentration of product or reactant per unit time. Don't forget the per unit time there, it's very important. Which experiment will have the highest reaction? It's experiment what? 2, right? Experiment 2. Use collision theory to explain your answer in 5.1. So the step number 1, what makes the experiment 2 to be? It has a what? A greater surface area. It has a greater surface area when you compare with this one, more especially. Those one are comparable. Greater surface area, and therefore there is more what? Collision per unit time. Don't forget that. Don't say more collision. Just say more collision per unit time, right? So that's the answer for this one. Right, it says besides temperature, write down one other way to increase the rate of reaction in experiment 2. In experiment 2, what you can do there other than the temperature, to increase the temperature there, you can increase the concentration of the HCl. Isn't it? This one is dissolved in HCl, so what you can do, you can increase the concentration of HCl, right? That's what you can do there. Now it says the mass of the gas produced in the experiment is obtained by measuring the loss of mass of the flask and its content. So this one, it's an open flask here with a magnesium powder and hydrochloric acid. In experiment 2, there's a hydrogen gas that is released there. But in order to measure that hydrogen gas that is released there, you measure the weight loss of the content. You must have the initial mass first, and then you have the final mass, right? So the difference between the two, it will tell you how much of hydrogen has been produced there, right? And here's the second part, the questions and the graph in relation to the experiment 2. It says the result obtained, results of the experiment displayed in the graph below. Now you have a graph. This is a graph of mass of hydrogen, which is the hydrogen that is produced when magnesium reacted the HCl. There's a hydrogen there that is produced. So this is the graph that shows the magnesium with time. It's a mass of magnesium with time. Do you see? As the reaction progresses, the magnesium is produced, the mass increases up until it stops, which is the reaction reaches completion. When it reaches completion, it means the magnesium has been used up completely. Do you see? The rate is faster here. It decreases until it stops there. Now 5.5, write down the name of apparatus Z. The apparatus Z, we are told it's a what? It's a flask. So it's a flask that now it's not just a flask, guys, it's a It's a conical. Conical, how do I write the conical flask, or an Erlenmeyer flask? I don't know how to write an Erlenmeyer flask. I think it's E-L, Ellen, oh wow, Erlenmeyer. I think it's written like that, guys. Check the spelling. Even if you said flask there, I think you get the marks. Give reason why this experiment setup cannot be classified as a closed system. Why? Because the hydrogen gas is escaping. It's not a close, because do you see it's open? The hydrogen gas is what is escaping there, right? Or you can say the flask is open. Flask is open, right? Now 5.7, it says calculate the average rate of this reaction during the first 4. So we wanted the first 4 seconds. So we wanted the average rate from there to there. So that means we can take this point and this point. At this point it's 4 to what? 3.5. And this point is 0 to 0, right? So let me calculate it here. The 5.7, the rate is equal to, here guys, it's going to be change in mass over change in time. Wait a minute, when does the rate equation have a negative? You have a negative if it's a reactant that you see. We're going to calculate the rate of hydrogen, and the hydrogen is what is the product. So it's going to be positive. You leave it as positive. But if it was you were calculating the rate of something in the reactant, you were going to put the negative here, right? I hope that makes sense. And then the rate, we're going to have the final minus the initial. We're going to have mass final minus the mass initial, which is T final minus T initial. And then the final is going to be 3.5 minus 0 divided by 4 minus 0. It's going to be 0.875 grams, and they told us what will be the units there. Even in the formula, the change in mass over change in time, we get it from there. It's gram per second. It's gram per second. We're done with that. Now it says write down the loss in mass of the flask and its content. You can get it. The hydrogen that is produced there, that means it's the mass that it lost there. So it's what? 3.5 grams, right? It says use the graph to calculate the mass of magnesium powder used in the experiment. So in 5.9 there, what you can do, they said use the graph to calculate that. So guys, if you can see there from the graph that it's 5.5, it's 3.5 the mass that they have lost there, right? So that means it's the magnesium, it's the hydrogen that it has lost. That's the mass of hydrogen, which is 3.5. So what I'm going to do the mole ratio. I'm going to convert the mass into number of moles. So say number of moles is equal to number of moles of hydrogen is equal to mass over molar mass, which is the mass is 3.5 divided by 2, which is where do we get the 2? It's 1 times 2 of hydrogen. It's going to be 1.75 mole, right? I've converted the mass of hydrogen, right? And then I'll do the mole ratio. Say magnesium is to hydrogen. The ratio there is 1:1. So 1:1. So the magnesium, it's 1.75, and the hydrogen is going to be 1.75. Therefore, we can say the number of moles of magnesium is equal to the number of moles of hydrogen, which is its 1.75 mole. Right? That means now we can change this number of moles into mass, because the question, it wanted the what? The mass of magnesium. The mass, sorry. And then we can say mass of magnesium is equal to number of moles times molar mass, which is its 1.75 times what? 24. Let me punch that in the calculator quickly. 1.75 times 24, it's 42 grams. Right? The question wanted the mass of magnesium powder used. Right? The mass of magnesium powder used. So it's 42 grams that is used there. Now it says why magnesium in experiment 2 is the limiting. Because it's used up completely. It is used up completely, or you can say, since we are told from the statement that HCl is an what? Is an axis. So that's what you can write there. You can say it's used up. Magnesium, it's used up completely, or you can say magnesium all reacted. 5.11, draw the graph given on your answer book and name it graph 2. On the same set of axes, draw the graph for experiment 3 and label this graph 3. Okay, 5.11.
So I'm drawing the graph that we already have. This is the hydrogen grams, mass of hydrogen, and then this is time in seconds. So it's 1, 2, 3, 4, 5, 6. Alright, and then it's 2.8 and 3.5. 2.8 and 3.5. So the graph is like that. It's like that. Alright, okay. It's not like that, it's like that. It's like this. Right? Where does it end in 4 seconds? Okay, let me end it in 4 seconds. Yeah. Come on. Right? So, this is graph 2. Now they say I must draw the graph 3. Now remember, 2 and 3, between experiment 2 and 3, the slowest is 3. So I must do experiment 3. The experiment 3 is going to start with the same, but it's going to yield lower. This is graph 2. Graph 3. Remember, the production of hydrogen there is going to be smaller. It's not specifically 2.8, I just made it smaller. I just made it smaller there. Not specifically 2.8 there. So it's going to have a low yield of what? Of hydrogen. This one, it will have high yield. What do you mean about yield? I mean about product, right? The amount of product. I hope, guys, this makes sense.
5.11, draw the graph given on your answer book and name it graph 2. On the same set of axes, draw the graph for experiment 3 and label this graph 3. Okay, 5.11.
So I'm drawing the graph that we already have. This is the hydrogen grams, mass of hydrogen, and then this is time in seconds. So it's 1, 2, 3, 4, 5, 6. Alright, and then it's 2.8 and 3.5. 2.8 and 3.5. So the graph is like that. It's like that. Alright, okay. It's not like that, it's like that. It's like this. Right? Where does it end in 4 seconds? Okay, let me end it in 4 seconds. Yeah. Come on. Right? So, this is graph 2. Now they say I must draw the graph 3. Now remember, 2 and 3, between experiment 2 and 3, the slowest is 3. So I must do experiment 3. The experiment 3 is going to start with the same, but it's going to yield lower. This is graph 2.
Graph 3. Remember, the production of hydrogen there, it's going to be smaller. It's not specifically 2.8. I just made it smaller. There. Not specifically 2.8 there. So it's going to have a low yield of what? Of hydrogen. This one, it will have high yield. What do you mean about yield? I mean about product, right? The amount of product. I hope, guys, this makes sense.
Let's look at question 6, the chemical equilibrium. It says the table below shows the effect of temperature changes on the value of the equilibrium constant when the following reaction takes place in a closed container volume of 500 dm3 cm3. So it's going to be 0.5 dm3 when we divide by 1000. Right, we're given that it's NO2, nitrogen dioxide, to that. The reverse, it's brown in color. The forward, it's colorless, right? Okay, now if you look at this table, we're given the temperatures in Kelvin and the equilibrium constant. If you look, as you go down the table, the temperature increases, but as you go down the table, if you look at the Kc values are decreasing there, right? You must remember, from the Kc value, Kc is equal to the concentration of product divided by the concentration of what? Reactant. Kc has it directly proportional to the concentration of product, right? So as the temperature increases, the concentration of product increases. But if you look here, as the temperature increases, the Kc decreases, right? Decreases. So if the Kc decreases, that means the concentration of product decreases because of the Kc value. Okay, let's answer the question. Define the term chemical equilibrium. The chemical equilibrium, guys, it's the dynamic equilibrium, right? Okay, let's put it like this. The chemical equilibrium is the chemical reaction where the rate of forward reaction is equal to the rate of reverse reaction. Stick to the exam guideline, guys. I might be paraphrasing it. Which color will be seen at 300, which is there? And what is the color that will be seen there? It will be colorless, guys. Not colorless. It will be light brown, because at the beginning we don't know which one is favored. It will start as the light brown. So 6.3 is the forward reaction exothermic or endothermic, right? So the forward reaction, guys, here it will be exothermic, right? Exothermic, the forward reaction. Why? It says explain your answer there. Explaining your answer, if you look at your Kc value, your first answer there, you'll say the Kc value, your Kc value decreases with increase in temperature. As the temperature increases, your Kc value decreases, right? And then you state the favor. So you say, since the products are not favored, because the Kc value decreases, the products are not favored. That means it's the reverse that is favored. So you will say the reverse reaction is favored, right, guys? Because the Kc value decreases, the concentration of product decreases. That means forward is not favored, it's reverse that is favored. So that makes it to be what? An increase in temperature to be the forward to be the exo, right? The forward to be the exo, right? It says in 6.4 x gram of nitrogen oxide is sealed in the nitrogen dioxide is sealed in the container at 300, which is at 300 Kelvin. The equilibrium constant is that one. At equilibrium, the concentration of nitrogen of this N2O4 was 3 mole per dm3. Calculated the x. The x is the mass of that, right? So the first thing that we're going to do, we have 3 at equilibrium, 3 mole per dm3 at equilibrium. It's N2, 4, and the ratio is 1 is to 2. No, the 2 is in this side. It's 2 is to 1. So at equilibrium we are told the product is 3, which is the concentration is 3, and we're given the volume there. So the volume from the concentration to number of moles were times by 0.5, so it's going to be 1.5, right? So to get this 1.5, let me write it. You're going to say 3, this one, which is times by 0.5 by the volume, you times the concentration by the volume, and to get the number of moles, which is 1.5, right? And then since it's 1.5 there, it's going to be 1.5 there as well, and then this is going to be 0, it's plus, right? Now having the 1.5 here, the 1.5, we can do the mole ratio. These are the number of moles. This was the concentration, and then you change that concentration into number of moles and the same number of moles. So this is the number of moles that is formed. So we can do the ratio of this number of moles that is formed to get the number of moles that is used there. So the ratio is 2 is to 1. So it's going to be that times that, right? This is x. It's going to be x. So it's 2. It's going to be 2 times 1.5. 2 times 1.5, it's going to be 3. So the answer here, it's going to be 3, right? And here we want the mass. The mass, guys, we know it's x. The mass we divide by the molar mass, which is for the nitrogen oxide, the molar mass is going to be 14 molar mass of nitrogen oxide. Nitrogen dioxide, it's 14 plus 16 times 2, which is, it's 46. So it's going to be x divided by what? 46, right? Okay, let me not do it that way. Let me not go that route, because it's going to be difficult if I take that route. Let's take an easy route where we say we have 3 here. So what are we going to do? Now we're going to use the Kc expression, because we have the Kc for the 300. This was at 300, so we're going to use that Kc in order to get the concentration here, the concentration there. So what are we going to do? Let me erase this. The molar mass, we're going to need it just a second. So I'm going to say Kc is equal to concentration of product, it's N2O4, and we divide by the concentration of nitrogen dioxide square, and the Kc, it's 1 times 10 to the power 1, which is, it's this one, right? And then we're looking for the concentration. We're looking for the concentration of nitrogen dioxide. So the concentration of this is 3. Where do we get the 3? This one, and we were given, right? So, and we wanted the concentration of nitrogen dioxide, it's a square, and then we cross multiply. So when we cross multiply, we will have concentration of nitrogen dioxide. Remember, it's a square there, so it's going to be 3 divided by 1 times 10 to the power 1, and then we put the square root in both sides. So it's going to be concentration of nitrogen oxide, it's going to be let me put it in the calculator. It's square root 3 divided by 1 times 10 to the power 1. It's going to be 0.5477 mole per dm3, right? This is what we're going to have it. We take this, we put it here, it's 0.5477, right? It's 0.5477, and then we put it there, and then this is the concentration. If you convert it into number of moles, you say 0.477, we times by half, which is the volume. The answer there, it will be say answer in the calculator times by 0.5, it will be 0.2738, right? And then having that, what are we going to do? So we'll say this, right, is the ratio. So we are looking for this number of moles. So we'll say, let's say this is going to be A. So we'll say A minus this is equal to that. So we'll say A minus 3, am I right? A, the initial minus used to give us what is remaining, which is at 0.2738, right? And then you take the 3 to that side, your A is going to be 3.2738, right? That's in what? That's in moles, right? These are the moles here. These are the moles here. So basically what you do here, you say A minus A minus 3. No, what am I doing? I'm looking for this, right? I'm looking for that, the initial. Normally you used to say that, yeah. We say it's A, right? So the initial number of moles, now it's going to be 3.2738, right? We got it. So now we calculated the mass. The mass of what now? It's a mass X, which is, this is X, right? Mass is equal to X is equal to number of moles times molar mass, which is the number of moles. It's 3.2738. We times by the molar mass of nitrogen oxide is what? Is 46. So the answer that you already have in your calculator, you times by 46. You times by 46, so you get what? 150,6 grams. So we got that. There are various ways, guys, to do that. Let's answer 6.5. How will the increase in reactant how will the increase in the reactant at 7 affects the reverse reaction? So guys, if we increase the reactant, right, the system is going to respond by decreasing it and increase the product. So they're asking how is going to how will increase the reactant affect the reverse. So the reverse is not favored. The system responded by decreasing the reactant. When you increase this, the reactant was decreased and the product was increased. So forward is favored, so the reverse is not favored. So the answer there is what? Is decrease. The answer is a decrease there. Now it says the pressure on the system is increased by decreasing the volume of the container at 300. So the pressure is increased. Now it says how will this affect the value of Kc? The value of Kc, guys, it's only affected by the, so it will remain the same. So you will say only temperature affects the Kc value. That's your explanation there. Your first answer is remain the same, and then only Kc affects. Now it says the concentration of product. How is going to affect the concentration of product increasing in pressure? We know increase in pressure. Let me remove this one.
Increase in pressure favors the side with the less number of moles, which is the concentration of product will increase and the concentration of that will decrease. So forward is favored there. So the answer there, the concentration of product, the answer is increase, and then you are left with 2 points using Le Chatelier's principle to explain. So you will say increase in pressure favors the reaction with the least number of moles, or you can say less of moles. That's 1 point. Second point, as I've mentioned, favors the side with the less number of moles, which is the product, which is the forward reaction. So the forward is favored. So you will say the forward reaction is favored. Right? That's important there. Guys, I hope this question makes sense. Let's look at question 7, the acids and bases. It says hydrofluoric acid, which is the HF, is a weak acid. Define the term weak acid. Weak acid is an acid that ionizes incompletely in water. It's very important to say in water, to form low concentration of hydronium ion, right? Okay, now it says a sample of hydrofluoric acid has a pH of 4,5 at 25 degrees. Now it says calculate the concentration of hydronium ions in the sample. So having the pH, will do the antilog. Concentration of hydronium ion is equal to 10 to the power negative pH. You get the mark for that formula, and then you say 10 to the power negative 4.5 is equal to 3,16 times 10 to the power negative 6, and the units are important, guys, there, mole per dm3. Right, now it says when hydrofluoric acid reacts with the sodium hydroxide, sodium fluoride is formed, and it says 7.13. Will the pH of the sodium fluoride, which is the salt that is formed, sodium fluoride, be greater than 7 or smaller than 7 or equal to 7? Right, what do you need to ask yourself? The hydrogen fluoride, what type of acid is that one? Is a weak acid. And then the sodium hydroxide is a strong base. So it's a reaction between the strong base and the weak acid. So the pH is going to be greater than 7. So the answer there is greater than 7. And then you say it's a what? Strong base reacts with the what? Strong acid. That's your reason there. Right, 7.2, it says reaction A, 3.5 of pure magnesium carbonate reacts completely with a 50 cubic centimeter of HCl. Alright, that means this one is a what? Is a limiting. If it says it reacts completely, that means an acid is going to be an excess. Alright, reaction A, we have a magnesium carbonate, and magnesium carbonate and HCl give you magnesium chloride and carbon dioxide and water. Now it says from this reaction the excess of HCl neutralizes. So what remained, remember this one is going to be a limiting and this one is an excess, so there will be something that will remain. What remained from this reaction is used to neutralize exactly 20 cubic centimeter of sodium hydroxide with a concentration of 1.2 mole per dm3. Right, now we have two reactions. Now in 7.2.1, Here's the reaction of HCl and sodium hydroxide. It gives you salt and water. It says calculate the number of moles of HCl reacted. The number of moles of HCl reacted, so we'll say HCl, number of moles of HCl reacted. Now guys, since we are given the 3.5 gram of that one, which is the amount that is used up completely, it can give us the amount of what? The amount of HCl, because in HCl we're only given the volume. So that means I'm going to change that into number of moles. The number of moles of magnesium is equal to mass over magnesium carbonate is equal to mass over molar mass. So the mass is 3.5. We divide by the molar mass of that, which is the magnesium is 24 plus the carbon is 12, and then the oxygen is 16 times 3. And then when I punch that in the calculator, it's 3.5 divided by 12.5 plus 16 times 3. So the answer there is 0.042 mole. Right, that's the number of mole. And then we do the ratio. The ratio there is 1:2. So is magnesium carbonate is to HCl. The ratio there is 1:2. And then we are looking for what? For HCl that reacted. The HCl, the HCl that reacted, and then we're going to put 0.042 there, and then we cross multiply. So your X there, which is the number of moles of what? Of HCl, is equal to 0.084 mole. Right, that's the HCl that reacted. That's the HCl reacted. Out of this 50 is the HCl that reacted. HCl reacted there. Very important. Reacted or used. Right, in 7.2.2 it says calculate the concentration of the original. So this is not the original, guys, this is what reacted from the original. So 7.2.2, it says what are we going to do here? We were told that the excess of HCl neutralizes 20 cubic centimeter of sodium hydroxide in 1.2. So we're going to use this sodium hydroxide to get this excess that is neutralized to. Now we're going to calculate the number of moles of sodium hydroxide using the formula that says N is equal to CV. And then the concentration is 1.2 and the volume is 20. The 20, when you divide it by 1000, it's going to be 0.02. And then if you say in a calculator 1.2 times 0.02, the answer is going to be 0.024 what? Mole. Right, this is the sodium hydroxide reacted. Now we're going to do the mole ratio. Sodium hydroxide is 2, and the mole ratio you can see is 1:1. So we can say the number of moles of HCl, it's HCl what? Which is it's an excess. We want to get the excess is equal to the number of mole of what? Of sodium hydroxide, which is same 0.024, because of the mole ratio is 1:1. So this is an excess of the hydrochloric acid. So if we want the initial, the HCl initial, now initial, so what do? We say the HCl, the one that is reacted, the number of moles that is reacted plus the number of mole that is what is an excess. We added the two, it gave us the initial. Right, the one that reacted, the HCl reacted there, it's 0.084, and then plus this one we just calculated 0.024. Right, I hope I make sense. And then when you punch that in the calculator, 0.84 plus 0.024 is equal to 1, no, it's 0,108 mole, right? So that's the number of mole. The question, it wanted the concentration. So what was the volume? Now we have the number of moles. What was the volume of HCl? It was what? 50. So we wanted the concentration, which is the initial. Now the initial concentration of what? Of HCl is equal to C is equal to N over V, which is the number of moles at 0.108 divided by the volume. The volume, it was 50, it's going to be 0.05. If you say answer divide by 0.05, it gives you 2.16 mole per dm3, right? So that's the concentration there. That's the concentration, the initial concentration. I hope I make sense, guys, by that. Let's look at question 8. Question 8, it's a galvanic cell, right? It says the diagram below represents a galvanic cell functioning under a standard condition with magnesium and iron as electrode. The net cell of the equation is this. Guys, do you see this is a galvanic, right? As I mentioned there, you have two half cells there, the magnesium and the iron. So we are given the half cell there. So in order to know which one is oxidizing and which one is reducing without going to the table, you can simply use the oxidation numbers. Assign the oxidation number here. The oxidation number is 3, and the oxidation number is 0, and the oxidation number is 0. The oxidation number is +2, right? So you can even tell the iron, what's happening to iron from 3 to 0. So 3 to 0, that means what's happening, there's a decrease in oxidation number. That means reduction is taking place. Let's look at magnesium. Magnesium from 0 to what? To 2. That means there's an increase in oxidation number. That means oxidation taking place there, right? So if the oxidation is taking place in magnesium, we know this electrode is going to be negative, which means oxidation takes place. It's an anox, right? And it's an anode, right? This side is an anode, and then this side is going to be positive. It's their cathode, right? And then the reduction is taking place. It's a red cat, right? And what else? The half reactions. The half reactions of this side, it's the Fe3. You can see from there, Fe3 plus, and it's getting what? 3 electrons and 3. It's gonna be 3, which is it start with Fe3 plus and then it ends with the Fe. We can even confirm that from the periodic table. Here is it. Here's the iron. We use that one. We do not use this one because it's Fe2 plus, that one. And there is another one that I want to show you. It's just that I can't see. We're not gonna use this one, even though it's Fe3 plus, but it ends with Fe2 plus, that one. We're not gonna use that one. And the magnesium is that one, right? So magnesium is oxidizing, so we're gonna write it this way, and the iron, it's reducing. We're gonna write it this way as it is there, right? Then let's go to magnesium. The magnesium, it's oxidizing. Do you see there's an increase in oxidation number? It's Mg and Mg2 plus 2 electrons. Remember, here in the galvanic, the one that is on the top, the half reaction that is on the top is oxidizing, and this one is reducing. Guys, I'm using table 4b here. Table 4b, remember. Right, let's answer the questions. The question, it says the energy conversion for this cell. Write down the energy conversion. The energy conversion here, it's from chemical energy to electrical energy, right? We're producing energy two standard condition. I guess I'm in a hurry. So it's the temperature. The temperature is 25 degrees Celsius, or in Kelvin it's 298 Kelvin. And then the concentration here, the concentration is the concentration of the electrolyte. It's 1 mole per dm3. Electrode 8.1, the electrode which acts as a cathode. Which electrode acts as a cathode? It's the Fe. It's the Fe, which is this one. It's the Fe electrode. So the answer is Fe. It says give reason for your answer. We can say reduction takes place. Reduction takes place there in the cathode. That's where the reduction takes place, right? Or you can say the Fe3 plus is a stronger oxidizing agent than what? Than the Mg2 plus. Guys, you need to write that in full. Just doing that to cut time. It says oxidation half reaction. We've already written it. It's gonna be this, right? And then the cell notation. The cell notation, we're gonna start with the anode. So the anode, we're gonna start with the reducing agent, which is gonna be Mg, and then change of state, and then it's gonna be Mg2 plus, and then the cell bridge, and then we're gonna start with the oxidizing agent, which is its Fe3 plus, and then the change of state, it's going to be Fe, right? There's no need to write the states, guys, and the concentration if you don't want to. Just save time not to write it like that. Name of the component responsible for the electrical conductivity in the cell. The component that is busy with that is the cell bridge. The cell bridge, what it does, it's responsible for the electrical neutrality in the electrolytes. 8.2, the last question. Calculate the E cell. The formula, guys, it's there in the formula sheet. It's E cell. Don't write your own. It's cathode. Write the cathode in full, minus E anode. Write the anode as in full as it is in the formula. Let's go and look. The reduction is this one, and the oxidation is that one. Okay, so there it's going to be negative 0.06 minus bracket negative 2.36. So when you punch that in the calculator, these two will multiply, and then it's going to be positive. It's going to be 2.3 2.3 volts. We are done with that. Now let's look at the question 9, the last question. It says an electrical cell represented below two carbon rods P and Q. So these are carbon rods P and Q there, right? Are used as electrode and concentrated copper chloride. So there's a copper chloride there. So in this solution there will be chloride ion when it dissolves this, and copper ions, and then we're given the source there. Remember, this is an electrolytic. It uses the power source. So this is negative and this is positive. It tells us this one is a what? Is a cathode. The cathode here is negative, and an anode here is positive, right? The anode, it's when the oxidation takes place. It's when the reduction takes place here. Now I'm not going to dwell on that.
In this one, it's a decomposition of copper chloride. You can check my other videos or just answer the question in this one. Define the term electrolysis. The electrolysis is a chemical process in which the electrical energy is converted to chemical energy. Here it's an opposite of a galvanic, but it is a chemical process. They're not asking an energy conversion here, guys. They're asking the term electrolysis. It's a chemical process that converts the electrical to chemical. Very important. What observation can be made at electrode P while the cell is operating? At P, guys, at P, what is going to happen? The cation, it's going to be attracted to the cathode. So what is going to happen? This Cu2 plus is going to be attracted and be reduced there and make a deposit there, which is a solid. So that's Cu2 plus, it's gonna be reduced there, which is gaining electrons, and become the Cu, which is the Cu in a solid state, is the one that you see there, right? So the observation that we see there, it's a copper. We see a what? A copper deposit. A copper deposit there. It's 9.2. So it's going to be a reddish brown copper deposit that we see there, or we see an increase in mass, right? In this side, guys, in this side you will see the chloride ion is going to be oxidized there, which is going to release electrons there because it's an anion. It's attracted to the anode, so there will be gas bubbles there. So this will be what? A Cu, a Cl, a Cl will oxidize it to Cl2 plus 2 electrons. So it's two of them. There will be a gas that is formed there, right? But they do not ask that. They ask in the cathode. Write down the name or the formula of the reducing agent. The reducing agent, you find it in the anode. The reducing agent is the chloride ion. So they wanted the name of the formula, so I'm going to write the formula. It's chloride ion with a negative, or you can write chloride ion. It's not chlorine, guys. Chlorine, it's this one, and this one is not a reducing agent. The reducing agent is that one. Now they say, what is the function of copper chloride as an electrode, as an electrolyte in the cell? You know what the electrolyte, what does it do? It conducts electricity. It conducts electricity through what? Through the movement of free ions or ions. Now it says this cell is now used for refining. Now this thing changes. Now it's the refining of copper now, right? It's no longer it's a refining of copper, right? So when the copper is refined, there will be a pure and an impure. Let me erase this now. Let me erase this. Okay, let me not erase. Let me erase this one. So here it's the now the cathode. What is happening in the cathode? The cathode, it's gonna be a pure copper. There will be a pure copper, and then in the anode there will be what? An impure, right? And the copper ions will oxidize, and there will be a pure copper that will be deposited there, which is the Cu2 plus will fall from that one, and then this Cu2 plus will be attracted there, and form the Cu there, right? Okay, now it says which electrode will have to be replaced by the pure copper. So as I've mentioned, it's gonna be electrode P, right? So it says give reason for your answer. You will say the pure copper um, is formed is formed in the is formed through reduction, right? Here there's a reduction that is taking place here, so this pure copper will be formed there, right? That's my reason there. And then explain why the concentration of ions in the solution remains constant. Guys, the copper ions are oxidized there and then they are reduced there. So it means that because of the rate of oxidation is equal to the rate of reduction, right? The last question of the question paper: silver and platinum are formed at the bottom of the container during the refining process of impure copper. So guys, here it's an impure sample, so it's copper that is here and platinum and what and silver, right? It's not only copper, it's silver. It's not only copper, it's silver and platinum that are there. So what's happening there? What is oxidized there? It's Cu. The Cu is oxidized there because it's a stronger oxidizing agent, and then the platinum and copper, they're going to fall and sit here at the bottom of the electrolytic tank. It's going to be platinum and silver, right? Now they say explain that, refer to relative strength of reducing agent, and explain why these two metals do not form ions. So they're not part of the electrolyte, they just sit there and form a what we call it a sludge. I'm not sure if I'm writing it. Now let's go to the table and check that. Here's platinum, there's silver, sorry, and the platinum is there. They said we must refer to the relative strength of reducing agent. So we're going to look at this side. The reducing agent is in this side. So when you talk about the reducing ability, you have to talk about this side. And let's note copper as well. Where is copper? Here's copper, right? So what are we going to say? Do you see these two? You see in this table there's an increase in strength of reducing ability. That means that these two, platinum and silver, are weaker reducing agent than Cu, which is a Cu is the one that is what is oxidized, is a stronger, this one is a stronger reducing agent, which means it's the one that will be oxidized there. So if you look at this impure, that contains, let's say in the beginning it contains the platinum and silver and copper. So the one that we're going to be oxidized there, it was what? Copper, than the two. So to write this, you're going to say the Cu is a what? Is a stronger reducing agent than what? Than platinum and silver, right? That's and Cu gets what? Gets oxidized. So that means it's the one that is going to lose electrons, right? Get oxidized to what? To Cu2 plus, right? That's the 3 marks, guys. Or you can say, alternatively, you can say there, Ag, silver and platinum are what? you can say are weaker. Weaker reducing agent. Weaker reducing agent than what? Than Cu. And Cu will and you can say these two, the silver and platinum, will not be oxidized. Will not be oxidized. It's going to be Cu that is going to be oxidized. Okay, I didn't say then what? Then Cu. Guys, I hope this question paper helps you a lot in preparation for your prelim or your trial exam. I wish you all the best. Take care. Cheers. Bye.